Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 24 kN. It is acting in the center. In the span BC also, there is a point load 12 kN. It is also acting in the center. The moment of inertia for the span AB is I. For the span BC, it is 2I. Length of the span AB is 10 meter. Length of the span BC also is 10 meter. In the point A, there is a fixed support. In the points B and C, there are hinged supports. The support in the point B sinks by 10 mm. The support in the point C sinks by 6 mm. The Young's modulus E is given as 12 kN per millimeter square and the moment of inertia is given as 125 into 10 power 7 millimeter power 4. The moment of inertia I is given in millimeter power 4. So we have to convert it into meter power 4. We know that 1 millimeter is 1 upon 1000 meter, but here we have power 4. So we have to divide this value by 1000 power 4. Finally, we are getting the moment of inertia in meter power 4. The Young's modulus E is given as 12 kN per millimeter square. We have to convert this value into kilonewton per meter square. Here we have mm square, so we have to divide by 1000 square. When we do that, we are getting in kilonewton per meter square. For our own convenience, let us multiply the moment of inertia and Young's modulus. When we do that, we are getting 15,000 kilonewton meter square. The settlement at B is given as 10 millimeter. Let us divide 10 by 1000 so that we will get 0.01 meter. In the same way, let us convert the settlement at C. When we divide 6 by 1000, we will get 0.006 meter. In this beam, we have to find three moments, MAB, MBA and MBC. Also, we have to find three reactions, RA, RB and RC. The point C is a simply supported end. In the simply supported end, there will be no movement. So MCB will be 0. Now let us find the fixed end moments. First, let us find them in the span AB. In the span AB, there is a point load 24 kN. This load is acting in the center. The formulas for the fixed end moments are minus WL upon 8 and positive WL upon 8. In the span AB, the support in the point B sinks by 0.01 meter. So we have to find the fixed end moments due to sinking of the supports. The formula to find the fixed end moments due to sinking is 6EI delta upon L square. The fixed end moments due to sinking will be either positive or negative. We have to find that. The fixed end moments due to sinking will be positive if the sinking occurs on the left side of the span. They will be negative if the sinking occurs on the right side of the span. In the span AB, the sinking occurs in the point B, so the sinking occurs on the right side. So the fixed end moments due to sinking will be negative. In the formulas, let us apply the values. W is 24, L is 10, EI is 15,000, delta is 0.01. The fixed end moments due to sinking will be same for M of AB and M of BA. So we can simply apply this value here. After the calculations, we are getting M of AB and M of BA. Now let us find the fixed end moments in the span BC. In the span BC also, there is a point load acting in the center. The formulas for the fixed end moments are minus WL upon 8 and positive WL upon 8. In the span BC, the support in the point B sinks by 0.01 meter. The support in the point C sinks by 0.006 meter. Now we have to find the net settlement. The settlement in the support B is higher than the settlement in the support C. So the net settlement occurs in the point B. To find the net settlement, we have to subtract this value by this value. When we do that, we are getting 0.004 meter. Since the net settlement occurs in the left side, the fixed end moments due to sinking will be positive. In the formulas, let us apply the values. W is 12, L is 10, delta is 0.004. For BC, the moment of inertia is 2I, so we have to multiply the EI value with 2. Here we have to be very careful. We know that the fixed end moment due to sinking will be same for both the M of BC and M of CB, so we can simply enter this value here. No need to calculate again and waste the time. After the calculations, we are getting M of BC and M of CB. In this beam, in the points B and C, there are hinged supports. So the number of supports where slope occurs is 2. In the point B, there is theta B, and in the point C, there is theta C. Now let us make the fully restrained structure. To make the fully restrained structure, we have to remove the hinged supports from the point B and C and replace them with the fixed supports. We have made the fully restrained structure. Now let us make the coordinates diagram. In this analysis, we have two coordinates. The first coordinate is in the point B and the second coordinate is in the point C. Because in these points only we have the unknown displacement, that is the slope. We know the formula to find the slope values. Delta matrix is equal to K matrix inverse into P matrix minus PL matrix. Inside the delta matrix, PL matrix and the P matrix, there will be two values. Because in this analysis there are two coordinates. Since there are two coordinates, the size of the stiffness matrix will be 2 cross 2. Inside the delta matrix, we will have the slope values theta B and theta C. P matrix is the final forces or moments acting in the coordinate direction. In the coordinates, there are no final moments developed because in the given beam, there is no overhanging. So inside the P matrix, we can simply enter 0, 0. In this formula, we have found P matrix. Now let us make PL matrix. We know that inside the PL matrix, we will have the moments developed in the coordinates due to the given load. Our first coordinate is in the point B. In the point B, we have found two fixed end moments, M of BA and M of BC. We have to add both of them. After adding, we are getting 13.2. Our second coordinate is in the point C. In the point C, we have found a fixed end moment, that is M of CB. Let us apply that. In this formula, we have found PL matrix and P matrix. Now we are going to make the stiffness matrix. Now let us see how to calculate stiffness matrix elements. For that, first we have to apply unit displacement in every coordinate. In this analysis, there are two coordinates. In the points B and C, we have the coordinates. In these coordinates, we have to apply the unit displacement, that is theta is equal to 1. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. We have to apply the unit displacement in the fully restrained structure, not in the given beam. Now let us make the first row in the stiffness matrix. For that, we have to apply unit displacement in the first coordinate. Our first coordinate is in the point B. In the point B, there is a fixed support, but when we apply unit displacement, we can assume that it becomes a hinged support, because in the fixed support, there will be no displacement. Now let us see how to make this curve. We are applying unit displacement in the point B. The point B is a joint. It is connecting the spans BA and BC. So we have to make two clockwise curves. One curve towards the point A and one curve towards the point C. Then we have to see the direction of the arrows and draw this curve. We have to give some gap between the fixed support and the curve, because in the fixed supports there will be no slope. Now let us find K11. For that, from the point B, we have to look on both the sides. On the left side, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of BA is 10. Let us apply that. Now let us look on the right of B. On the right of B also, there is a fixed support. So we have to apply the same formula, 4EI upon L. The moment of inertia for BC is 2I. So instead of I, we have to apply 2I. Length of BC is 10. Let us apply that. For K11, there are two stiffness values. We have to add both of them. After adding, we are getting 1.2 EI. Now let us find K12. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, there is a hinged support. If the fair end is hinged, the formula for the stiffness is 2EI upon L. Length of BC is 10 and the moment of inertia is 2I. Let us apply them. Finally, for K12, we are getting 0.4 EI. Now, let us find the second row in the stiffness matrix. For that, we have to apply unit displacement in the second coordinate. Our second coordinate is in the point C. In the point C, there is a fixed support, but when we apply the unit displacement, we can assume that it becomes a hinged support. Let us see how to draw this curve. We are applying unit displacement in the point C, so we have to make a clockwise curve towards the point B. Then we have to see the direction of the arrow and draw this curve. We have to give some gap between the fixed support and the curve, because in the fixed support there will be no slope. Now let us find K21. For that, from the point B, we have to look on both the sides. On the left side there is no slope curve. If there is no curve, there will be no stiffness. Let us see on the right side there is a hinged support. If the far end is hinged, the formula for the stiffness is 2EI upon L. Length of BC is 10. Let us apply that. The moment of inertia for BC is 2I. So instead of I, we have to apply 2I. Finally, for K21, we are getting 0.4 EI. Now let us find K22. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, there is a fixed support. If the far end is fixed, the formula for the stiffness is 4EI upon L. Length of CB is 10. Moment of inertia for CB is 2I. Let us apply them. Finally, for K22, we are getting 0.8 EI. In the stiffness matrix, we have found both of the rows. Let us apply the values. EI is constant. Let us keep it outside. In this formula, we have found everything. Let us apply the values. We can add these two matrices. After adding, we are getting this. EI inverse is 1 upon EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find the inverse of a 2 by 2 matrix, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we can multiply these two matrices. After multiplying, we are getting theta B and theta C. Now let us make slope deflection equations and then apply the values of theta B and theta C and find the final moments. First, let us make the slope deflection equations in the span AB. In the equations, let us apply the fixed end moments. Length of span AB is 10 meter. Let us apply that. In the point A, there is a fixed support. In the fixed support, there will be no slope, so theta A will be 0. After applying the value of theta B, we are getting MAB and MBA. Now let us make the slope deflection equation in the span BC. No need to make for MCB because we know that it is 0. Only we have to form the slope deflection equation for MBC. In this equation, let us apply the fixed end moment. The moment of inertia for BC is 2I. So instead of I, we have to apply 2I. Length of BC is 10 meter. Let us apply that. After applying the values of theta B and theta C, we are getting MBC. In this analysis, we have found all of the moments. For MAB, we got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we got a positive value. That means it is acting in the clockwise direction. Finally, for MBC, we got a negative value. That means it is acting in the anti-clockwise direction. Now, let us find the reactions. First, let us take the span AB and find the reactions. By taking moment about B, we can find RA by applying the rule sigma V is equal to 0. We can find RB1. Now let us take the span BC and find the vertical reactions. By taking moment about C, we can find out RB2. By applying this rule, we can find RC. In the point B, we have found the reaction 2 times. Let us add RB1 and RB2 so that we will get RB. Now let us make the shear force diagram. Now let us use these formulas and make free movement diagram. Then using the end moments, we can make end movement diagram. Then we have to combine the free movement diagram and end movement diagram so that we will get bending moment diagram. Now we are going to end this session. Thank you for watching this video.